Good day to everyone. So in the last video, we have discussed about the introduction about the surface tension. So in this video, we are going to discuss about the pressure difference across the different liquid surfaces and how to calculate the excess pressure inside a curved surface and the related problem. So before going into that, suppose we have taken the two different liquids. One is the water, so another one is the mercury. Suppose if you take this is water and this is mercury. Suppose if you take a one glass tube and if you place in the water as well as the mercury, so you can see the two different scenarios can be occur in the water as well as mercury due to the surface tension. So in this water, what happened is, suppose if you dip the glass plate or a glass tube, you can see this water is actually clinging into this glass tube upwards. That is, the water molecules cling to the surface of the glass and the water molecules rise along the plate like this shown there in this figure. Suppose if you plot the tangent line to this cling surface, you can see that there is some angle. So this angle is actually known as the angle of contact. Okay, so that is can be measured as a theta. And this is happening in this water because the adhesive force is actually comparably larger than the cohesive force. That means the interaction between the water molecules, two water molecules, is lesser than the force of attraction between the water molecule as well as the gas molecule. Sorry, the glass molecule. Therefore, the water molecule, the water is actually clinging upwards to cling with the glass tube. On the other hand, suppose if you take the glass tube, dip it into the mercury, what happens is you can see that the angle of contact is actually different from the mercury. You can see that this is, so the mercury molecules actually cling to the surface and the liquid is depressed along the plate shown in this figure, so that you can see that the plate is actually having this, and the water is actually having this kind of shape. Or if you have a glass tube inside this mercury tank, you can see that this kind of shape, the molecule, the mercury is actually filled with like this a shape, whereas for water it is actually showing like this. So for water it is actually going the concave like shape, and for the mercury, the mercury rises into this glass tube like making the convex kind of shape. And if you again plot a tangent line along this surface, then you can see this the angle of contact is larger than the water. So this angle of contact theta can be defined as the angle made by the tangent at the point of contact of the liquid surface with the glass surface inside this liquid. So this angle of contact is actually varying from 0 to 180 degrees. For example, if you take the pure water, so the pure water is actually will not cling with this glass, so that you can see that there is a horizontal shape between that means in the pure water, the angle of contact between the glass and water is actually 0, so it has a horizontal line. However, suppose if you take the water with some small impurities, you can see this kind of shape, so that the angle of contact for the water is actually varies from, that means for the water, the angle of contact is actually less than 90 degrees, the theta. However, for the mercury, usually for the mercury, the angle of contact is in the range of 140 degrees. So the angle of contact is actually depends on the nature of the liquid and the solid which we are actually pouring the liquid. It is quite independent of the angle of inclination of the solid and as well as the liquid to the liquid surface. So based on this, the angle of contact, you can see the liquid surface can be defined in three different categories. One is the horizontal plane, another one is the concave like shape, and another one is the convex kind of shape. So you can see that like this. So suppose if this is filled with a liquid, so you can see the three different angle of contact. So one is the horizontal and concave and the convex. So if the free surface is the liquid surface is actually plane, then the resultant surface tension on the molecule of the surface is actually 0. So the surface tension for this the horizontal, the plane is, the liquid plane is actually 0 if it is actually the horizontal line. Suppose if you consider the liquid is actually making the concave like shape, then the resultant surface tension is actually acting upwards. That means, means vertically upwards. That means the resultant force due to the surface tension on molecule on the surface is act vertically upwards. On the other hand, suppose if you consider the surface of the liquid is actually convex, then the resultant force due to this surface tension is actually down acting on the molecules and the vertically downwards to the molecules of the surface, the surface. So suppose if you consider a liquid drop or a soap bubble, so the soap bubble or liquid drop having the spherical shape, so that means the surface tension acting actually inwards towards, vertically downwards in the soap bubble or a liquid drop. Therefore, the excess pressure actually inside comparably inside it's having the excess pressure than the outside. So we are going to derive the expression for how to find out the excess pressure inside the liquid drop. Okay. So in order to find out the excess pressure, we are going to consider a spherical liquid drop which is having the convex shape as shown in this figure. The molecule is actually near the surface of the drop experiences the resultant force only in the surface of the molecule, surface of the bubble. So that so the resulting force is actually acting inwards due to this surface tension as shown in this case. So therefore, the pressure inside the drop must be greater than the pressure outside this liquid drop or a liquid or a soap bubble or a bubble. So let us consider this excess pressure inside the liquid drop over the pressure outside is actually taken as P. That means the pressure difference between the inside the liquid drop as well as outside the liquid drop is taken as P. And if you imagine this liquid drop is actually divided into two equal parts, equal halves, so that the equilibrium of the upper half, that means the half of the semisphere of the drop is actually shown in this figure, which is having the radius of r, and the surface tension in the surface is taken as a sigma. So this r is the radius and sigma is the surface tension. So that the upward force on the plane of this the plane which is actually mentioned as the ABCD due to this excess pressure P can be written as, so the upward force so due to the excess pressure P, which can be given as P times of the area pi r squared. So similarly, so the downward force due to the surface tension acting along with the circumference of this circle ABCD can be written as, so the downward force due to this due to the surface tension along the circumference. So we know that the surface tension is given as a sigma and the circumference is taken as the 2 times of 2 pi r. So that is the downward force due to this surface tension along the circumference of the circle ABCD. And since this upper half of the hemisphere is actually in equilibrium, so that I can equate these two forces, upward force as well as the downward force, that is P times of pi r squared, which is equal to sigma times of 2 pi r. So this pi will get cancelled and this 1 r and this r will get cancelled, so that the excess pressure P can be given as 2 times of sigma divided by r. So this is the excess pressure in the liquid drop. Suppose if you consider this is actually a soap bubble or a water bubble. So the excess pressure on the water bubble or a soap bubble. So we know that this liquid drop is actually having the inside this inside the liquid is everything is means the liquid drop is actually inside everything is a liquid. There is no air. It's in the possibility of the air inside this liquid. However, if you consider the soap bubble or a water bubble, so it has two liquid surfaces. So with in contact with the air, one is the inside the bubble and another one is the outside the bubble. Therefore, the force due to the surface tension, which is equal to 2 times the pressure, 2 times of 2 sigma into 2 pi r. Therefore, which is equal to 4 times of pi into r into sigma. So this is the force due to the surface tension in the soap bubble. And if I again consider this soap bubble, the one half of the hemisphere is actually in equilibrium with the equilibrium, then we can equate this p times of pi r square, which is equal to 4 pi r into sigma. Again, this r and this will get cancelled. Sigma and the pi and pi will get cancelled, so that the excess pressure P it can be written as 4 times of sigma divided by R. So this is the excess pressure in a soap bubble. However, for the water, the liquid drop, the excess pressure is actually 2 times of sigma divided by R. So from these two expressions, we can easily identify that the R is actually inversely proportional to this pressure. That means the excess pressure inside the drop or a bubble is inversely proportional to the radius. Therefore, the pressure needed to form a very small bubble is very high. Or if you consider as two liquid drops, is having one is a small one and another is a large one. So the smaller bubble having the larger excess pressure inside the bubble. That is why, suppose if you consider a balloon or a liquid bar, a soap bubble. So once it's very hard to blow the balloon initially. So once the balloon is actually start growing, then it is very less air pressure is required to make it expand it. That this is the reason for this case. So for the small bubbles or a small drops, the pressure inside the bubble is actually very large. Okay. So next we are going to find out what is the excess pressure inside any curved liquid surface. So as we already discussed that, suppose if you consider a flat surface, then the excess pressure, the pressure inside and outside this liquid surface is actually same. However, suppose if you have the curved surface, whether in a convex or a concave, then for the convex, the resultant force actually acting upwards, and for the concave, it is the resultant force is actually acting downwards. And if we consider a curved convex type of surface, then the pressure inside must be greater than the pressure outside and the excess pressure inside this liquid drop or a soap bubble is actually balancing the force of the surface tension. So in order to find the excess pressure of the curved surface, we are going to consider a rectangular surface, and the rectangular element is actually given by the A1, B1, C1 and D1 of the liquid surface. Here this A1, B1 is the length, and the B1, C1 is actually taken as a breadth. So the A1 and B1 is having the curvy surface, and this curvy surface is having the radius of curvature R1 from the center O1. Similarly, this B1, C1 is also a curved one, and this radius of curvature is taken as R2, which is actually meet the center at the point of O2. And if you consider the small p is the excess pressure inside the surface over the outside, then the outward thrust. So the outward thrust on the surface of A1, B1 and C1, D1 can be given by the expression the pressure into the area. So the area of A1, B1, C1 and D1. So this is the formula. Pressure into area is the formula for this thrust, so that we can write this outward force for this liquid element, which we have considered as a P into area of the element A1, B1 and C1, D1. So which can be given by P times of P into this area can be given by since it's a rectangular element, so we can take the area is actually taken as L into B. So length is taken as L1 and breadth is taken as B1, so that I can write this as L1 into B1. Now if we consider this surface is actually moved upwards with a very small distance of delta x, so that this A1, B1, C1 and D1 is actually moved in upward direction like this. So this is a moved surface. Let us take this as a moved surface. So this is actually taken as A2 and this is B2, C2 and D2. So the distance between the movement is actually taken as a delta x. Therefore, the new position of this position of the surface is taken as new position of the surface is taken as a A2, B2, C2 and D2. Therefore, we can find out this the work done to move this surface from from the original position to the new position is taken as the work done in the displacement. From the older position to the new position, which can be equal to the outside thrust into the distance. So the thrust is which will be given by P into L1 B1 into the distance it is moved, which is actually taken as a delta into x. So this is the work done in the displacement. Let us take this as equation 1. So now we can easily find out what is the increase in the surface, increase in the surface area. So increase in the surface area, which is actually equal to this area of this A2, B2, C2, D2. So area of A2, B2, C2 and D2 minus the area of A1, B1, C1 and D1. Suppose if you consider this length is actually now changed as L2 and this is taken as a B2. So then I can find out the increase in the area of surface, which is equal to this is actually L2 into B2 minus L1 into B1. That is the increase in the surface area. Suppose if you consider the two similar triangles, that means A1, O1 and B1. Similarly, A2, O1, B2. So the two similar triangles, that's A1, B1, O1 and A2, B2, O1. So this is actually the same triangles but with a smaller displacement, so that I can write this A1, B1 divided by A2, B2, which is actually equal to this A1, O1 divided by A2, O1. Or I write this equation. I write this as A1, B1 is actually L1 and A2, B2 is actually L2, which is equal to A1, O1. So the distance between the A1 and O1 is actually taken as the radius of curvature R1 divided by this A2 and O2 is actually this R1 plus delta x. So that I can write this A2 and O1 is actually R1 plus delta x. Therefore, from this relation, I can easily calculate what is L2. So the L2, which is nothing but the L1 times of R1 plus delta x divided by R1. Or I can rewrite this as L1 into 1 plus delta x divided by R1, since this R1 will be equal to 1 plus delta x divided by R1, so that L2 which is equal to L1 into 1 plus delta x divided by R1. That is the length of this new element of A1, A2 and B2. Similarly, if you look at the other surface of this B1, C1 is actually now become a B1, B2 and C2. Again, if you consider this O2 is the radius of curvature is for this triangle B1, C1 and O2 is taken as R2, and the increase in the distance is taken as a delta x again, so that I can find out the B1, B2. So it means the B2 which is equal to B1 into 1 plus delta x divided by R2. Therefore, the area of L2 into B2 can be written as L1 into 1 plus delta x divided by R1 multiplied by the B1 times of 1 plus delta x divided by R2. And I can rewrite this as L1 into B1 into multiplied by the 1 plus delta x divided by R1 plus delta x divided by R2. So that is actually the L2 and B2. Therefore, now you can substitute this L2 B2 into the increase in the surface area equation. That means L2 into B2 minus L1 into B1. So we know this, what is the value of L2 and B2 here from this expression, so that I can write the increase in surface area, which is actually equal to this L2 B2 minus L1 into B1, and this L2 B2 can be given as L1 into B1 1 plus delta x divided by R1 plus delta x divided by R2 minus L1 into B1. And if I expand this form, we get the L1 B1 into 1, you will get the L1 B1, and this L1 B1 and minus L1 B1 will get cancelled, so that finally the increase in surface section area can be written as L1 into B1 into delta x divided by R1 plus delta x divided by R2, or if I take this delta x as outside as a common, so that I will get 1 plus R1, so the L1 B1 into delta x into 1 by R1 plus 1 divided by R2. So that is the increase in the surface area. So that the work done in increasing the surface area can be written as work done in increasing the surface area can be given by the surface tension multiplied by the increase in the surface area. So the surface tension into increase in surface area. That is, we already found out what is the expression is, so that we already know the surface tension is marked as the sigma. The surface tension is sigma multiplied by this increase in area is L1 B1 into delta x 1 divided by R1 plus 1 divided by R2. That is the work done in increasing the surface area. Let us take this as the equation 2. Therefore, if I try to equate this equation 1 and 2, so this equation 1 is actually the work done in the displacement, and equation 2 is actually representing the work done in increasing the surface area, so that I can equate this equation 1 and 2, that is P into L1 B1 into delta x, which is equal to sigma into L1 B1 into delta x 1 divided by R1 plus 1 divided by R2. So here this L1 B1 delta x, and the right hand side also we have a L1 B1 delta x, which will be cancelled, so that the excess pressure can be given as sigma into 1 divided by R1 plus 1 divided by R2. So this is the excess pressure inside the curved liquid surface. So the excess pressure inside any particular surface can be deduced from this equation. Suppose if you consider a spherical liquid drop. So first we consider the spherical liquid drop. Or you can consider the air bubble in the liquid. So either you can consider a spherical liquid drop or a air bubble in a liquid. So it has only one surface, and the radius of curvature is actually same as everywhere because of the spherical radius. So that this R1 which is equal to R2 which is equal to, suppose if I take this R as the radius of the air bubble or as a liquid drop, then I can substitute this value into this equation, so that the P which is equal to sigma times of 1 divided by R plus 1 divided by R. So we will get the 2 divided by R. So the P is equal to 2 times of sigma divided by R. So which is what we have derived earlier in the previous expression for the liquid drop case. Similarly, for the spherical soap bubble, so spherical soap bubble, here the area of contact of the bubble the area of contact with the air with the soap bubble is actually twice here, so that the excess pressure can be given as 2 times of sigma. So the 2 times of sigma into 1 divided by R plus 1 divided by R again, because R1 and R2 are equal to the radius R because of the spherical shape, so that I can write P is equal to 4 times of sigma divided by R. Okay. And the third case, suppose if you consider the cylindrical drop, suppose the water drop which we have considered the cylindrical drop, then the radius r1 can be taken as r, that means the radius of the cylinder, and the r2 is actually here infinity here because it's a cylinder, it's having the infinite number radius, so that r2 is actually equal to infinity. So therefore, if I substitute these values into the previous equation, P is equal to sigma divided by r, so r2 will be infinity, so that we get the 1 here, so that the final answer P is equal to sigma divided by r. So this is the excess pressure inside this cylindrical drop. Suppose if you consider the cylindrical bubble, again you have a two surfaces actually contacted with the air, so that P is equal to 2 times of sigma divided by r is the excess pressure inside the cylindrical bubble, because in this bubble you have two different surfaces actually in contact with the air. Therefore, using this equation, the excess pressure equation, you can easily find out any particular surface. You can find out the excess pressure. You can detect the excess pressure from any different particular surface. Now let us discuss some of the related problems related to this excess pressure. So the first problem is, so there is a minute circular hole at the bottom of a small hollow vessel. So the vessel has to be immersed in water to a depth of 0.4 meters before any water penetrates inside. So find the radius of the hole in the surface tension and the density of the water be 73 into 10 power minus 3 Newton per meter, and the density is given as 1000 kilograms per meter cube respectively. So we have the height is given as 0.4 meters, and the surface tension of the water is given as 73 into 10 power minus 3 Newton per meter, and the density is actually 1000 kilograms per meter cube. So if you consider this problem, the water cannot penetrate till the hydrostatic pressure is greater than the excess pressure that comes into play due to the surface tension. So that this limiting condition, when the water actually just penetrates inside this vessel, the two pressures should be equal. That means the hydrostatic pressure as well as the excess pressure, it should be equal. That means the hydrostatic pressure can be given as H rho G, which is equal to the excess pressure. So the excess pressure can be given as 2 times of sigma divided by r for a vessel. So here the r is the radius of the hole which we have considered. So that from this equation I can easily find out what is the value of r. So r is equal to 2 times of sigma divided by h into rho into g. So this is the expression to find out the radius. So here what is the given as sigma is equal to 73 into 10 power minus 3 Newton per meter. That means the surface tension of the water. Similarly, the h is given as 0.4 meters, and the density is given as rho is equal to 1000 kilogram per meter cube. So we have to find out what is the value of r here from this expression. So I can substitute all these values in this equation. So r, which is equal to 2 into sigma is 73 into 10 power minus 3 divided by h is 0.4 meters, and the rho is given as 1000 kilograms into 9.8, and g is actually given as 9.8. so that if I calculate the final value, which is equal to 3.724 into 10 power minus 5 meters. So this is actually the radius of the hole. Next, the second problem which we are considering is, so what would be the pressure inside a small air bubble which is having a radius of 10 power 5 minus 4 meters situated just below the surface of the water. So the surface tension of the water may be taken as 70 into 10 power minus 3 Newton per meter, and the atmospheric pressure can be given as 1.012 into 10 power 5 Newton per meter squared. So here we can consider the spherical air bubble, and which is actually over the small atmosphere, so that the excess pressure can be given as P is equal to 2 sigma divided by r. So here the sigma is given by 70 into 10 power minus 3 Newton per meter. Similarly, the r is actually given by r is taken as given by 10 to minus 4 meters. So the excess pressure can be given by that can be calculated using this equation. P is equal to 2 into 70 into 10 power minus 3 2 into 70 into 10 power minus 3 divided by 10 to the power minus 4. So the final answer is 1400 Newton per meter squared. So this is the excess pressure inside this small bubble. So from this equation, you can easily find out the total pressure. The total pressure is nothing but the atmospheric pressure plus the excess pressure. So the total pressure, this is equal to atmospheric pressure plus the excess pressure. So the atmospheric pressure is already given in the problem itself, and we have calculated the excess pressure. So the atmospheric pressure is 1.012 into 10 power 5 Newton per meter square, plus the excess pressure we have calculated is 1400 Newton per meter square. So that the final value is equal to 1.026 into 10 power 5 Newton per meter square. So this is the total pressure inside the total pressure of the small bubble. So next, the third problem is, so the pressure of air in a soap bubble is of 10 power minus 3 meter diameter is actually given by 8 into 10 power minus 3 meters of water above the atmospheric pressure. So we have to calculate the surface tension of the soap solution. So here the pressure is not actually directly given, but it is actually compared with is actually given by as 8 into 10 power minus 3 meters of water, so that we have to convert this water pressure into the excess pressure, means the excess pressure we have to calculate from this value, and then after that you have to substitute the value into this excess pressure formula. So the excess pressure inside the soap bubble over the outside is actually given by P is equal to 4 sigma divided by R. So here the P is actually given by 8 into 10 power minus 3 meters of water. So that we have to just compare this into this with the water. That means 8 into 10 power minus 3 into the density of the water is given by 1000 into the G. This is 9.81 Newton per meter square. So that the final value will be equal to 78.48 Newton per meter square. So this is the excess pressure of the soap bubble which we have considered. So that using this P, we can easily find out the radius is already given here. The radius is R is equal to 7 into 10 power minus, that means the diameter is actually given here, 7 into 10 power minus 3. So that you can find out the radius just dividing by 2, so that you will get 3.5 into 10 power minus 3 meters. That is the radius. We have a pressure, so that you can easily calculate the sigma. So you can just rewrite this equation in terms of sigma. So the sigma which is equal to PR divided by 4. So the P is given by 78.48 into the 3.5 into 10 power minus 3 divided by 4. So the final value will be equal to 68.67 into 10 power minus 3 Newton per meter. So that is actually the surface tension of the soap bubble, the soap solution, which we are considering in this problem. So I can solve one more problem, final problem. The fourth problem is, so two soap bubbles of radius R1 and R2, which is actually coalesce with the to form a single soap bubble, which is having the radius of R. Suppose if the excess pressure is given as a P, you have to prove that the surface tension of the solution to form this soap bubble is given by this relation sigma is equal to 1 divided by 4 times of P times of R cube minus R1 cube minus R2 cube divided by R1 squared plus R2 squared minus R squared. So here the pressure inside the first soap bubble is actually given by, so the pressure inside the first bubble, which can be given by, that is taken as P1, which is given by the 4 times of sigma divided by R1 plus the atmospheric pressure, that means P, that means I taken as a P. Okay, so that is the pressure inside the first bubble. Similarly, the pressure inside the second bubble, which can be taken as P2, that means equal to 4 sigma divided by R2 plus the atmospheric pressure P. Sorry, this P is actually excess pressure. Similarly, these two bubbles are actually coalesced and to form a single bubble which is actually larger than these two, so that the pressure inside the larger bubble, that can be written as P3, which is given by this 4 sigma divided by R, because the R is the radius of the bubble, plus the excess pressure P. Okay. So when we consider this wall V1 and V2 are the volume of the two smaller bubbles, and V3 is the volume of the larger bubble formed. So that according to this Boyle's law, we can write this P1 V1 plus P2 V2, which is equal to P3 and V3. So this is the Boyle's law, which you have already studied in your previous classes. So that I can write this P1 V1 and just substituting the values of P1 V1 here. So the P1 is 4 sigma divided by R1 times of plus P into volume is actually volume of the sphere is given as 4 by 3 pi times of R1 cube, plus similarly the P2 V2 can be given as 4 sigma divided by R2 plus P into 4 by 3 times of pi into R2 cube, which is equal to 4 sigma divided by R plus P into 4 by 3 pi R cube. So if you cancel out the common terms and simplify this equation further, the final answer will be 4 sigma in times of R1 squared plus R2 squared minus R squared, which is equal to 3 times of R cube minus R1 cube minus R2 cube. So from this we can easily find out the sigma which is equal to 1 by 4 times of P into R cube minus R1 cube minus R2 cube divided by R1 squared plus R2 squared minus R squared. So which we have proved that sigma is equal to this value. Okay, let's stop here. So the remaining portions we can see in the next class. Okay, thank you.